Thanks for listening in today. It's been a few months since we've talked to you, and we're excited to jump right back in. Today, we're talking about serviceability of batteries. And it's really important when you're designing a product to think about that full life cycle, and even more important because lithium ion batteries in general have safety issues when you're thinking about reuse or using it in a product that's different today than it was originally designed for. And so today we have Mr. Luke Workman.
Hello.
Hello. I'd like to ask the first question, which is what is the concept of designing for serviceability?
Yeah. Um, the principle of it is sounds beautiful in the event you had a defective cell somewhere or that there was a problem, uh, say environmental or mechanical damage. Um, then you could disassemble that, remove the problem afflicted region, replace just that problem afflicted region of the battery. Maybe it's defective cells, maybe it's a bad connection or corrosion. Reassemble that pack and use that pack again since perhaps 98% of the cells in it were unaffected. Um, so this is why it's a tempting and appealing thing, because people think, like, I won't have to replace whole batteries. I'll just have to replace individual cells or modules from the battery.
There's so much mining, time, money, energy that goes into building a battery pack. I could understand why people would want it to be serviceable. My question, as far as like the history, and only say what you know, can you think of a serviceable product out there that maybe this kind of idea came from for batteries?
If you look at an internal combustion engine, you you can almost blow it up unlimited times. A few times I pushed connecting rods through the sides of the block, and it's not worth repairing it. But um, you can break your sleeves and re-sleeve the block, and you can spin your bearings and your mains and your rod bearings and remachine these things and have a new engine that functions just as well again after rebuilding. Uh, Battery packs are not this way, unfortunately.
So, what would be the positives of designing a battery for cell serviceability in theory? You kind of touched on that, talked about mining, and then how can we design batteries to meet those design requirements if we can? It's a big question.
It is a very big question, and the short answer to the question is no. You you won't meet those requirements, and the longer answer to it is a longer no of why, once the other cells and other modules in the pack have aged and reached a given impedance, uh, they won't share current uniformly with a replacement module. So uh, not only would you need to have a serviceable battery, you'd need to have an aged supply of modules. And it gets worse than that too, because the method of aging affects uh, the cell's impedance increase relative to its capacity loss. So, for example, packs that were decayed by just sitting at a high state of charge at a high temperature have a different type of impedance decay than packs that were deep cycled regularly.
It's really hard to match. So we're kind of talking about cells, modules, and packs. And so let's say talking about an electric vehicle, you have a pack that's usually made up of a bunch of different modules. And if you replace a module within that pack, what happens to the rest of the battery?
If that module is part of a parallel cell group and you replace it with a cell group that has lower impedance, it'll asymmetrically sink and source the majority of the current through that portion of the pack. This will cause not only temperature imbalances, but cell wear imbalances and premature degradation and failure of that pack assembly.
So is it a safety issue at that point, or is just really you're sentencing that battery to die an earlier death?
Well, if you had effective BMS control to observe that uh, the replacement module was asymmetrically burdened with this current, you could hopefully shut it down before it was a safety issue. However, you would have a lower performance product, from that moment forward. Um, in the event that all modules are in series and you replace a module, this is your best case scenario for replacement modules. You have less issues with current sharing, and the issues become ever effectively having top or bottom balance correlate with the rest of the pack from that point, which is a lower concern. And again, with a good BMS, that can largely be managed out to be transparent to the user.
So you're saying going deeper into that module, like let's say a module failed, but we know that it's maybe one cell that got through quality control for some reason and got put into that module. What would happen from the cells within that module all the way into the pack? Like, would that one cell being changed, like what is the downstream effect of all that?
You can add, depending on the type of failure that the cell has, that single cell added can kill the pack, the whole pack, if that cell is defective. This is one of the reasons why it's so critical to screen your cells before building the pack with them, because no amount of battery management algorithm or integrated tech will actually replace a defective cell for you. So let's say that you have the condition where the cell has a parasitic internal self-discharge, and this internal self-discharge is lower than the current to fuse, say, a bond wire that pack may have had for cell level protection. Then that cell will kill the rest of the cells in parallel with it, dragging them all down with the self-discharge of that defective cell. In this situation too, the best thing that the BMS can do is not to try to correct that problem, because again, it can't repair a defective cell. The best thing the BMS can do is not allow the user to charge the product at that point so that it will die a graceful death.
So what does it look like from BMS data for someone to program their BMS to make sure that if it notices that?
What you see in BMS trends in that case is all bleed resistors are being used except for one bank. So that implies one bank is having its own bleed occur, not through the BMS, through an unintended means, current leakage path there. Intracell or intramodule. Intramodule being surface corrosion, condensation, condensates electrolyte path, and intracell being manufacturing defects, coating defects, impurities, separator perforations. Lots of things can cause defects that result in self-discharge. Too many to list in a video.
Yeah, okay. As far as I understand that getting the right cells, screening the cells, making a module is really the most ideal case, right? If I'm a battery manufacturer, I want to build something, send it out into the world, and pretty much not think about it until it's basically has no capacity in it that it can't really be used anymore.
That's best case.
That it is best case. As you know, in life, it's not always that ideal scenario. So there are people or businesses out there that maybe get cells that are not at the best grade, or maybe are not super clear on where they came from. Hopefully that's not the case, but let's say they, for that reason, they're like, okay, if one cell dies, I want to make sure to replace that. Other than the cell slowly killing the module and the kind of the effects that you put there, from a design standpoint, that kind of changes the way the cells are held, how there's environmental protection of that battery. What kind of compromises are made to make it serviceable to design, and why or why not would that be an issue?
I would say on that the start of this use case you mentioned, where someone may not have a high quality cell supply or doesn't understand the supply chain route for their cells. I would say they should not make a product or ship it in that situation, for the reason that each cell is a potential safety hazard liability. Someone's home, a forest fire, a life safety issue. And so if you don't have good quality control and awareness of the quality control processes, I would say that's negligence personally, and you shouldn't ship that. And that kind of comes down to the situation where folks say, well, we want to be able to run trash cells and swap them out when they die, but really you can't ship a product with trash cells. That's like a 1 month business idea or something, until fires end you.
That's fair. It kind of makes me feel like I have my foot in my mouth even asking that question, because I definitely agree with you on that perspective. I think what I was trying to get at though is I've seen like e-bike makers, for example, like being at some sort of show somewhere, where they kind of like scoffed at me when I was like, well, what do you mean you're going to replace your LG cell, just for example, because they knew where it came from. They had a great cell supply, but this engineer was very set on being like, well, I want to switch out a cell in the, rare case, or he didn't really know what case, how often it would happen. But for some reason, that got put into the design requirements for him to design to. And so, what I'm trying to ask you is like, no matter what the reason is, right? You always need to dig into like, why is a design requirement there? But somehow that finds its way into some people's battery requirements. So why or why not is that a good idea?
I think it brings up a really good point. I've had two major operations that required cell level serviceability, and it's interesting for both of them. First, in data centers, they have 4,000 amp hour 2-volt lead acid cells in large series strings to make 48-volt UPS batteries for telco backups. And you are capable of replacing any cell in the string, just a single 2-volt cell out of the string. In practice, when they have a cell fail, they replace the whole string each time, for the reason that they're paranoid if one of them failed that another one was close to failure. And this is a situation where they had cell level replaceability the whole time, maybe at the best, most advantageous level you could have it, being a lead acid in individual 2-volt cell groups, and never took that opportunity to do single cell replacements again, because when they work their fault analysis and they say, well, this cell in this spot died already once, and that means the cell next to it from the same lot, made under the same conditions, out of the same materials, imposed under the same stress, may also be just about to fail, and that's not worth the risk of replacing one. They replace the whole set. That's data centers now, where cost is a lower concern over reliability and continuous operation being the highest concern that they're willing to pay anything for. The second application would be my first job doing motorcycle batteries. It was requested that each cell could be replaced, so that if there was a defective cell or if there was a problem with a cell, you could disassemble that battery and replace that cell, rebuild the battery, and continue on your way. So built a system capable of this, and unfortunately, not only was the ability to swap cells never utilized, for the reason that it was quickly learned in testing that adding a new cell into that parallel cell group with aged cells, had that significant current asymmetry, which prohibited uniform temperature operation and prohibited operating in a way where the pack would have a long life. The other downside is that when something is made to be disassemblable, it has a series of interfaces intrinsically, because you have portions with surfaces that will be disassembled. And so everywhere that these surfaces contact, water vapor and capillary effect, surface energy wicking causes condensates to want to climb between these surfaces, travel down these surfaces. So all of these interfaces that are sandwiched up against each other want to have the the surface energy of that surface relative to water causes it to intrude and wick throughout this assembly. Water that is in interfaces, unfortunately, when you have the product on a hot sunny day again, it doesn't dry out from inside those interfaces for the reason that water can only evaporate out of non-saturated boundary layer humidity conditions. And so when you're in a crevice volume, you have a boundary layer saturation and you have very low boundary layer exchange. And so for this reason, you have effectively a one-way trap. So when you make an assembly that's a series of clamped interfaces, you've made a capillary path and a one-way trap to collect condensates, which leads to corrosion and failure.
Yeah, basically you want to test your cells, put them in there, and make sure that they're happy without one-way traps.
And the best way to do that, there's many ways you could offer to do that. For example, it's easy to say, well, just make a hermetic vapor tight seal, on the enclosure. And of course, on paper that works out great. We just have no vapor exchange and gas diffusion. But of course, in practice, even if you could pass a helium leak test when you leave the factory, this would be a product that requires maintaining pinhole defect, leak-free state through its service life, which for many applications things get bounced against rocks and driven over curbs and hit by road debris, all the sorts of things that affect a product in the real world. If it's on a bicycle, they get crashed, all kinds of things happen that induce pinhole-like defects or seal interface-like defects that are usually invisible to the human eye even to recognize that a seal has been compromised. This is why my favorite method for solving that risk hazard, abating that risk hazard, is monolithic encapsulation in a polymeric resin compound, so that all the voids, all the spaces that water would want to wick into, you've already flowed a potting into those regions, and that potting is a complete encapsulation of all of those surface interface vulnerabilities, so that you've encapsulated the assembly, both from, this effectively eliminates your ability to rework or replace cells in the assembly, but the beautiful thing is it actually gives cells an opportunity to reach end of life by being worn out from charge and discharge, until their capacity fades, which is the best thing that can happen to cells. When they're built to be taken apart and serviced, you will find you're often doing it and quickly experiencing rapid failures and fires.
I've met some designers that violently oppose potting. There seems to be kind of like two different camps and batteries. There are ways to mitigate weight, mitigate a lot of the issues that kind of come up. So again, it kind of comes back to those first principles of what are you designing your battery for? Are you designing it to survive its long life until its cells wear out? And how do you do that? Another thing I was thinking of too is I used to feel like we were paranoid about the whole like vapor intrusion of batteries and whatnot. And I know that you've sifted through plenty of battery ashes to really feel confident in that. But it wasn't until we spoke to people who make tanks for gases like hydrogen gas and things like that, and liquid hydrogen, that they were the ones that kind of scoffed at us and were like, yeah, nothing's ever sealed. And these are like the people that are like making serious tanks, right?
Yep, inches thick of carbon fiber tanks, and you get a acceptable permeability.
Right. And so to think your battery is not like inches of carbon fiber on the outside.
Yep. And whenever you think you've achieved a seal on something, you just haven't put it in a sensitive mass spec because you are leaking like a sieve out of all seams on anything you've built that you thought was sealed, unless you happen to build crushed copper con-flat knife edge joints, in which case you might have actually achieved seals if you did a perfect job on mating them.
I'm excited to see how manufacturing technology continues to evolve in our lifetime. So, talking a little bit about how batteries might fail when it comes to designing for serviceability, why is it important to monitor pack isolation?
That's a great question. I think isolation is your most useful vital sign of the health of a pack. Um, it's often overlooked, and I used to be annoyed that it was a requirement to have to measure it when I first started in industry. But now I consider it, it's like checking the pulse, for the reason that if you see asymmetries in your isolation between positive to negative to chassis, uh, this shows you a signature of an ionic path that's begun. So it gives you this warning that a corrosion pathway has formed prior to it going molten and ionic conduction levels, at which point you have a fire in seconds. So this is a early, advanced warning system. I find tracking isolation value for some EVs is it would work as an acceptable hygrometer to quantify the humidity in the atmosphere on a given day, for the reason that you observe the saturation change and ionic change in the corrosion paths. So no one's ever achieved perfect isolation to chassis. You achieve some number of orders of magnitude where it's hopefully not a shock hazard and not a rapid decay hazard. But even if you have, say, 10 mega ohms of isolation to the chassis, 10 mega ohms with just 1 volt across it is still tens of billions of electrons per second, because you're dividing by the number of electrons in a coulomb there. These electrons' motion, is driving ionic breakdown, electrolysis, dissociation of bonds in dielectrics, crazing dielectrics, so that they decompose and become resistive rather than insulative like they're supposed to. For example, many epoxides do this under voltage stress and time, slowly become resistive, and then become sharply resistive if you migrate enough ions adequately through them.
And for our technical listeners, did you go into how to measure isolation, or is that kind of just a big topic?
I mean, yeah, there's countless ways to measure it, but I love to do a method if I've got my own tools with me, not just using the BMS, which usually a BMS will simply connect a resistor between high side of pack to chassis, connect that same resistor to low side of pack and chassis, and look for the difference in voltage drop across it to use Ohm's law to solve for the missing impedance of the chassis isolation there. My preferred method to do it, since that value just gives you a pseudo-ohmic value, my preferred method is to use cyclic voltammetry, connecting to chassis and sweeping up, say, 1.5 times pack voltage, and then I sweep down 1.5 times pack voltage, and I look for a difference in current and an offset. And if you see either of those things, you have a path that's not a resistive path. For example, your best case when you have an isolation defect is that it was something like carbon dust or a type of rubber that uses carbon black in it to become conductive or something, and it has a weak true R, not an ionic R. But in the event, and so if you run cyclic voltammetry, you would see perfect symmetry if it was, a true R. But when you see asymmetries and when you see an offset, then that is the sign that you have a non-true R. You have a pseudo-impedance, an ionic impedance, and in this case, that the pack has an issue that, if not dealt with, is not only a potential fire hazard, but if you develop a hard isolation short and it's not on something accessible, the pack is done. It's time for recycling. And by hard isolation fault, I would say anything below 100 kiloohms is a hard isolation fault to me.
There's a lot of like rhetoric that kind of goes around. Like someone was telling us the other day that somebody bought all the GM packs from the Chevy Bolts and like want to make new stationary storage with them, which is cool. Like those are pretty much brand new batteries. And so like my question is, I've seen something in like Australia where people are using like Nissan Leaf packs and making those stationary storage. Again, that's to me that's not like designing something from a first principles idea where you're like designing stationary storage from the ground up to be stationary storage. But I understand wanting to be thrifty and using those materials that have already been mined, because recycling is kind of a pretty intense thing as well too. um, how would you test a battery to make sure that it's safe for a second application?
That's a great question. And before I even measured capacity or impedance on the pack, I would run isolation hypot cyclic voltammetry on the pack housing to see whether or not it was worth even bothering to measure electrical performance of that battery. If those things came back clean, then you'd want to run a cycle on it, and you'd also want to perform EIS on it and observe. I'd do a double pulse test too. You'd want to observe impedance behavior, capacity retention, and you'd want to understand that under your use case profile with its aged impedance that you weren't inducing hazardous temperatures under your use case. And yeah, those would be the first checks. Obviously, you'd want to then look through BMS logs or have your own BMS logging for signatures of defective cells. Like I mentioned, if there's a cell group that's never had the bleed resistors come on when all the other ones come on, then those are giveaways that you wouldn't want to bother using that pack in your assembly because it will just need to be replaced soon as that cell group finishes being killed by its self-discharging cell.
If it were me, I'd want the second life application to be pretty pampered, right? Because even if you did all that, I'd still want it to be like basically air conditioned and pretty low humidity.
I think they will need temperature and humidity control if they wanted to even have a shot at it, and they may want to do something like. I was shocked how long it takes when you put a battery in a vacuum chamber to get the water out of it, but they may even want to do something like a low temperature vacuum bake out on the packs for days or even weeks before loading them into that temperature and humidity controlled warehouse, just so if they had latent condensates that hadn't yet formed a detectable bridge path in the housing, that they wouldn't build up a warehouse around having one bad pack. In the warehouse battery of reuse, it has the same problems that a cell maker has. What if I put in one bad cell, right? And then it cost them the whole pack. But in the warehouse battery, it's what if I put in one Leaf pack that had a defect I didn't know, or one Chevy Bolt pack that had a problem I didn't know, even though all the other Chevy Bolt packs may have been fine. You lose the whole warehouse, So it's a risky thing. Obviously you could design rooms partitioned and have physical footprint between the partitioned areas and everything to try to not lose the whole assembly.
I don't know of one machine that basically does all the tests that you're suggesting for Second Life as of yet. Like I've seen a lot of really cool ideas on how to address different portions of what you're talking about. So even if we ran all those tests you're suggesting, and then even more, right, if you put more thought into it, would you feel comfortable putting that in your garage while your parents were sleeping above your garage? Sorry, your parents are angels, so.
Personally, uh, I would only feel comfortable if it was a potted assembly, for the reason that, and even then, just potting alone doesn't solve your problem if you pot in the wrong material. So, uh, been there, done that. But it's critical that it's encapsulated in something that won't degrade from electrostatic field forces and ionic migration over time. And so, yeah, personally, I wouldn't want a second life ESS in my home or my parents' home, unless it was something that had been potted in.
So are you saying that, like, let's say, because I don't think the Chevy Bolt pack, I haven't seen a new one, is potted or anything like that. Let's say somebody opened it and they were like, I love this material. And you were like, I love this material too. And then they potted it, they ran on the test you were suggesting. Would you feel comfortable with that? Or is there still just kind of like some risks that are just unknown?
That's a good question. Once it was potted, and if it was potted in the right material, something like a urethane urea hybrid, and or with endothermic fillers to improve thermal runaway resistance, um, in that case, I would be all right with it. Uh, yeah, I think the risk is fairly low at that point. You could make the argument the risk is lower at that point than on a brand new battery that was just made, for the reason that infant mortality type defects would have already fallen out. And say if it had cells with impurities, manufacturing defects to cause self-discharge, those would have already manifested in a pack failure too. So in some ways you have a proven piece of hardware uh, at that point, and in other ways you have some associated risks. The reason I say that is, if prior to it being potted in its life, relative surface motion between cells and components, especially when they're not potted monolithically to be a rigid assembly together, they have surface motions, and things like aluminum surface motion next to dielectrics. It forms aluminum oxide on the surface, sapphire, which grinds into nearly all types of softer materials, which is about everything but diamond. So um, yeah, there could be mechanical vibrational damage. There could be things that were close to causing a mechanical failure, dielectric breakdown, decomposition. And hopefully once you potted it, you would put the progression of that type of failure mechanism on hold, and hopefully it would never break through. But it's a non-zero risk. Um, but it's perhaps arguably as low as the new battery risk, which is a non-zero risk as well, because you could have had latent defects that weren't screened, undetectable screen defects.
Like common sense visual check that should be done as well
Oh yeah,
after you run all those tests.
yeah. And I would disqualify packs that have signs of uh, flood damage, mechanical damage, corrosive exposure damage, abnormal thermal, heat exposure signs. All of those things I would cull the pack for without even beginning electrical testing, for the reason that you really need a battery to be perfect, or you don't want to have it. There's no there's no good place in your life for untrustworthy batteries. They're too much of a risk and liability. I guess unless you're a battery recycler, in which case there's a place for them in your life, which is going into the blast freezer in the mouth of the shredder to shred them to recover the materials in them. But that's the place for batteries which have experienced damage. Batteries which aren't perfect should go in the shredder.
So there's still the kind of like common sense visual check that should be done as well after you run all those tests.
There's a good outcome you can have there, though, if the intended use case was something that's a rough use case, let's say. Then going into a Second Life application might mean that they're way overqualified, which would be a benefit in that situation.
Thank you. And kind of what I was mentioning earlier, as far as like as people get more access to batteries and they're out there and they're degrading and hopefully they're living a great first life. Like, I'm open-minded, but I definitely see a really good case for designing batteries for its intended use. So the question I was going to ask is, when would you choose reuse or over recycling?
If they were, obviously, if I had an application for it that had value to use that energy storage capability, and assuming it's potted so that it's not a corrosion vulnerability and vapor intrusion condensation vulnerability. Um, I would say I would do it for a pack that just had low capacity, or and maybe capacity down to like 85% or so, and impedance as high as say 150% of new impedance. The reason, someone might say, well, my home only needs this much power. My whatever application only needs this much power. Why do I care about the impedance being right? And the reason is that cells fall off a cliff um, pretty sharply. It's a very nonlinear. The slope out towards 80% might be pretty long and flat, and from that area they generally slope downward sharply. And so the reason I wouldn't mess with one that was below around 85% or plus 150% impedance is you wouldn't you would have a short period of time before it too was falling off the cliff. So I feel like it would be wasting your time. So maybe you'd even want it to be 90% of new capacity to make it worth messing with it. But again, that would depend on the individual's application.
Yeah, there's a lot of time to test it, make sure it's good, add all the new components, make a whole new product. That's essentially a business, right? So you'd want to get your return on investment if you were doing reuse there. I'm not sure if people do stuff other than like Burning Man art cars, unless you're kind of economically positive.
I'm a scientist, so I'm not appropriate to give business advice, but I wouldn't want a business advice that involves a waste stream that has hazards associated with it of what the customer may have exposed the product to before you got it that you don't know. Uh, Whether you're shipping something that's a time delayed incendiary device or not. So I was phrasing it under the context that someone was going to use it for personal use as their second life. Yeah, if you're going large scale with second life, you better come up with an excellent screening process, and then also partition. Maybe 10 or 20 packs to a room that you've got, cinder block walls with enough space between the cinder block walls so that you can validate if you lose one room, you don't lose the entire room, the entire warehouse, right?
Would you give that same advice for a new battery?
Good question. Yeah, you'd want to design similarly for a new battery too, and especially you'd want to screen your cells so well. You know, the the best screening data is original formation data from the manufacturer, and hopefully, if you're on good terms with them, they're binning your cells well based off of that formation data. But the second data that you've got an obligation to get is that open circuit voltage after it's sat during shipping from the factory. You know, if you see suppression in some cells, this is a sign of a defect, and the defect for internal self-discharge mechanisms can be lower than the threshold that's caught by a formation machine. And that's not even the formation machine's fault. They can, it can be a very insignificant amount of current over the scale of 24 hours, but a very significant amount of current and off-gassing and related decay over a period of a year or a period of 2 years, right? Which is why you don't want to put it in the product before catching that, or you'll replace the whole pack.
Is there anything that you could say that would make people feel more comfortable about lithium-ion batteries in general?
They're made very well today. The amount of quality control, the amount of materials, purity and testing of slurries and coating and rolling and stacking, the ability to capacitively, electrostatically, and with high pot test validated jelly rolls, mechanical and electrical integrity prior to filling it with electrolyte. It's an amazing ability to screen, and then of course, as we mentioned, the formation process. So yeah, cells have never been safer from a manufacturing perspective and a manufacturing quality perspective. Uh, this won't make you feel better, but there is a trend that there's kind of two camps in industry right now. The camp going increasingly high nickel fraction in their cathode, and the camp going LFP, iron phosphate cathode. And the folks going increasingly higher nickel, these cells are getting feistier and feistier as they push energy density and they push cobalt out. Cobalt is a stabilizer that if you want a really safe, rugged cell, you want a decent amount of cobalt in it if you're doing a ternary battery. And so in this case, in some ways, cells are becoming more fierce as they increase their nickel quantities, and this makes thermal runaway behavior more violent. And the other side of it, though, is to balance that, the iron phosphate cells being made, are having a very stable cathode with no thermitic decomposition failure mode. So it's a gentler type of runaway. And so it's good to see iron phosphate becoming more mainstream in EVs.
Yeah, it's generally nice. At least I know there's other factors that go into it, like the manufacturer, how it was tested, any damage to it. Like there's definitely any risk with any lithium ion cell, but generally LFP is pretty nice. I do like to see that, and hopefully there's alternative to lithium in homes. I mean, we talked about stationary storage a lot because that's kind of the use case for serviceability eventually, right? So we've seen some really cool stuff come out of even India. We've seen some cool sodium cells, and we're really excited about the future. At least from a safety perspective, those are some of the safest cells we've ever seen.
And on the topic of sodium cells too, with a sodium iron phosphate cell, there's nothing of rare abundance. Everything in the cell is a super high earth crustal abundance element, which means you can scale that to have battery double conversion UPS backup of the whole power grid if you wanted to. It's not a materials or physics limitation. It would just be a matter of people choosing to build it.
I think we could do a whole talk on just different kinds of batteries. Is there anything else that we want to talk about with serviceability?
The areas of your pack that you may not want to encapsulate, and again, this is up to the battery application, or encapsulate in something that's non-rigid. The fuse and contactor of the battery, these are parts which sometimes may need to be replaced, and the battery pack is otherwise perfectly fine, other than that the fuse and contactor had something unexpected fail them. In this situation, that's the only access port, and even having the busing to enter that area for the contactor and fuse, that busing needs to be encapsulated in potting leading up to those joints. And then wherever you have joints that, you can either soft pot it in something like a gel which remains weak enough you can push your tools into it, push your hands into it to change the contactor and fuse out when you need to, or rip the material out and then re-pour it afterwards. Or you space them far enough apart and then validate it yourself, so that nothing can use surface tension to allow drops of water or capillary wicking effects to bridge points in that assembly. So water can bridge 2 points. It depends on the surface energy of the point and the geometry of the point, but a water droplet can bridge a gap, that's say 8 to 10 millimeters apart, and it can stretch across that surface and maintain bridging those. So if those are between different voltage potentials, this rapidly consumes one side as an anode by electrolysis, piling up those electrolysis products on the cathode side, growing this bridge into solids reaching towards each other from what was once just a drop of water between it. So if you're going to have any areas that are unpotted, like I mentioned, a fuse and contactor area perhaps that aren't potted, in that case you've got to have, there's a book, and there's tables that say creepage and clearance charts, but they are, I was going to say complete bullshit, but they're just designed around a circuit board behavior. When you have long paths, for example, you can have points that are 3 inches apart in your little fuse holder assembly, contactor holder assembly, So from a creepage and clearance table, it would say, you can be a whatever 50,000 volts or whatever between these points without an issue, right? But in reality, uh, if there's a dribble of water that can wet those two surfaces at the same time, then it doesn't matter that they're 3 inches apart. You rapidly induce electrolysis, consuming one side until failure. This is why creepage and clearance kind of tells you whether or not it instantaneously causes a problem. But I I manually take an eyedropper and my finger and also use surface tension modifying agents too to make water extra sticky and you know, physically bridge different points and confirm that there's no combination of liquid arriving in that assembly that results in points being bridged. And only then do I allow, once you can fire hose that assembly out happily, spray that assembly with sticky corrosive liquids happily, and know that nothing happens, then you know that that area for the fusing contactor in your pack is safe to be a replaceable unpotted portion of the battery.
I'm so glad that you brought that up, especially talking about serviceability. We're really talking about the cells area, and you talked about even the portions of the battery that lead to the cells. But I think having a contactor or fuse fail is a lot better than having the rest of the battery fail.
Yeah, those are the two pieces that are the exception to the rule on nothing at all being serviceable in a battery. But again, you can by you could have a situation where you chose to make the contactor and fuse serviceable, and because of that, you had to recall the whole product line. If you didn't undergo a validation like I brought up, where that whole area needs to be uh, designed to be friendly, with water break tabs, protruding geometry tabs, so that you can't make a electrolysis pathway through that unpotted area where you can replace those assemblies. Otherwise, in any unpotted zones that have voltage and busing in the assembly is a failure waiting to happen, right? It's just condensate away from a fire or a product failure.
And you have a lot of great equipment here that can test fuse blow curves, contactors, just because you have a lot of experience seeing those not always be totally correct with the data sheet and them acting a bit different in real life.
The carry current of a fuse is a thermal function of heat in to heat out. So the amount of heat out on the busing to it has a direct relation to the carry current. And that's why we validate them all in application with the representative busing to ensure it has the intended performance.
I also really appreciate you bringing up the fact that sometimes it's really great to leave the digital world. And when you're making hardware, you really need to have your hands on it. It's not just simulations and data sheets.
I've been disappointed from looking in CAD and thinking there was no way water could bridge different points because there's, X much distance between them. Then you run the test and lo and behold, it wicks along the edge, wicks along that seam, wicks up this seam, and you have a electrolysis pathway. It's definitely something you want to confirm and measure hands-on.
Well, Luke, I really appreciate your time today. I think this has been a great conversation. We look forward to seeing, or I look forward to seeing the future of serviceability and recycling. And I mean, getting more batteries out there is great for everyone. Thanks so much.
I agree. Blessings.